The disodium pentasulfide alpha phase is a unique phase that exists within a composition range of about 66.5 to 71.5% sodium for a temperature range from 0 to about 265 degrees Celsius. At 20 degrees Celsius, it has a brown-yellow color. Disodium pentasulfide has several industrial uses, which include acting as a chemical fungicide, as a blackening agent on copper jewelry, as a component in a polysulfide bromide battery, as a toner in a photochemical solution, and in the tanning industry to remove hair from hides.
A few more of its uses are related to other polysulfides. It is the molecule that they are manufactured from, and can also act as a melt to determine their electrochemistry.
Disodium pentasulfide is produced by taking a molecule that already has sodium in it, such as disodium sulfide, sodium hydrosulfide, or sodium hydroxide, and having it react with pure sulfur. One method, for example, is to take disodium sulfide and sulfur and dissolute them in a solvent such as ethanol or ammonia. The solution is evaporated, and then disodium pentasulfide crystallizes. The bonds between the sulfur molecules are covalent nonpolar single bonds, whereas the bonds between sodium and sulfur are polar single bonds. This is because sulfur is more electronegative than sodium, meaning that they are more likely to accept electrons to fill up their valence shells. The molecule overall is not polar. The structure of disodium pentasulfide phase is orthorhombic. There is no particular parent phase for this phase because this composition becomes a liquid with no intermediate phases as the temperature increases. Short, unbranched polysulfide chains are the preferential form of sulfur and sodium polysulfides, which contribute to the stability of these materials. This phase also has a density of 2.08 grams per centimeters cubed at 20 degrees Celsius. The role of defects in this material are essential to understanding it. Vacancies increase the entropy of the crystal. A self-interstitial defect introduces relatively large distortions in the surrounding lattice because the atom is substantially larger than the interstitial position in which it is situated. In the application of disodium pentasulfide for molten salt batteries, the removal of liquid sulfur from the electrode surface in the two-phase region is important in order to achieve high specific energies. The solution of the problem requires ways to improve the mass transport properties within the graphite matrix. This can be achieved either by increasing the mass transport rate of sodium sulfides to the solid electrolyte and/or the rate of sulfur removal from the electrode surface.
The disodium pentasulfide phase is highlighted on our diagram.